Week 2, Wednesday. Here we are. Okay. So we left off, and on Monday, we optimized a function using, Monday we did cross-validation, okay? It was last week, we talked about finding the optimum by taking gradient, setting it equal to 0, and whatnot, okay? All right, so we have been using the mean squared error as a way to measure our objective function. Our objective function, the thing that we are trying to optimize, and in our case we're trying to minimize this function, is the mean squared error. We want to pick the values of W0, W1, whatever weights go into our model. We want to pick those so that the mean squared error is as small as possible. And so for linear regression, it's just a matter of picking the slope and the intercept so that these squared residuals are as small as possible. And if it's multiple linear regression, if you've got a quadratic or cubic term, it's the same kind of idea. Pick the W's so that the mean squared error is as small as possible. What we've done is we said, all right, well, let's take the gradient of the loss function with respect to our weight vector W. We set that gradient equal to 0, and we solve. And I imagine a lot of you have already done this as part of your first homework problem, right? It's just we've changed the loss function now has like an A matrix somewhere in there, okay? But then you're going to take the gradient with respect to W, set it equal to 0, and solve, okay? And that's fine. That's fine. That works well, especially if the loss function is fairly simple, not too complicated. The way we find it, not too bad, okay? A lot of times, though, the loss function gets more complicated. And later on in this course, we'll take a very, very, very shallow introduction, but an introduction to neural networks nonetheless. And inside for a neural network, the way you calculate the loss function gets a little bit more complex. And in that case, it gets harder to find the gradient. And even if you do find the gradient, it might not be easy to set it equal to 0 and solve, okay? Because that's like a whole nother problem, right? So figuring out the gradient, that's one thing. But then setting it equal to 0 and solving for that, that's a whole nother issue. And so when we run into something like that, the way we solve, or the way we try to minimize, is we'll take an iterative approach or a computational method to do it, okay? And so this is what we're going to do. We're going to fit our model. And what we want to do is we want to figure out the weights or the parameter estimates that are going to minimize that loss function. We always treat the data as fixed. The data comes in, and we're trying to find the weights that basically optimize the data, all right? And so your data might be the entire data set. It might be a portion where you've subset to a training set, right? And then you've left out the validation set or something like that. But whatever it is, whatever your data is, you're going to treat the data as fixed, and we're picking the weight parameters to fit that particular set of data. Okay, so these weight parameters aren't going to be the best solution if you bring in another set of data. Okay, and that makes sense, right? If somebody else brought in different data, you'd probably get different slope and intercept parameters. Okay, so the loss function is going to be a function of the parameters that we need to estimate. And for linear regression, if we're only estimating slope and intercept, our loss function is affected by the slope and the intercept that we choose, right? It's kind of like you have those two knobs, one that controls the slope, how steep it is, and one that controls the intercept, where it goes up and down. And that's going to affect the mean squared error there, okay? In 102A, at least if you took it with me, we covered coordinate descent, okay? And we said you turn it into univariate things and you optimize. I think you do coordinate descent in the other classes as well, right? Okay, well, I don't know. All right. And so in our class, Right now, though, we'll talk about gradient descent. Gradient descent is another iterative computational method for finding an optimum. Okay, so it might be helpful to think about just the univariate case. Okay, for a single variable, the derivative represents the slope of the tangent line at some point x. And if you have a multivariate function, if you have a function of several variables, then the gradient is kind of the analog of the derivative. And it is going to be a vector that points in the direction of greatest increase at some point x. Okay? And the magnitude of the gradient is the rate of increase in that particular direction as defined by that vector. And the idea behind gradient descent is that if you're at some location, you find the gradient, and that's going to point you in the direction of greatest ascent. Okay, it's going to point you uphill. And basically, we're going to say, well, we're going to go downhill by going in the opposite direction. Okay, so if that way is uphill, then we go in the opposite direction, and that will point us downhill. Okay, and basically, we just take a step downhill, and then we repeat the process. You take a step downhill, you calculate the gradient, and you say, okay, which way is downhill? You take a step downhill. And that's it. You just keep going downhill, 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 downhill. And eventually, you should get to the bottom of something, at least a local minimum, we hope. Perhaps you run into a saddle point, perhaps something else, you get stuck for some other reason. But the idea just being, if your instructions are keep going downhill, you should end up at the bottom of the hill. And so the gradient descent algorithm is incredibly simple. It's just this one line right here. Okay? You have some function f of w, and this is the function that we're trying to minimize. In our case, it'll be our loss function. The mean squared error is going to be represented by f of w, right? It's a function where the input is this weight vector w. We're going to put in a slope, we put in an intercept, or whatever terms that we need, and that's going to spit out how much our mean squared error is at that point. What we do is we say, okay, we start off with some arbitrary value for the slope and the intercept. So maybe we start off with a slope of 0 and an intercept of 0. Okay, so we're just having a flat line, y equals to 0. And we say, okay, does this do a good job of fitting the data? We calculate the mean squared error based on using this flat line 0, y equal to 0. And it says, no, this isn't doing a good job. And we could get better values if we adjust the slope, if we adjust the intercept. Okay, how do we do that? Well, we're going to take our current estimate, and then we just subtract off the gradient at w. So we calculate the gradient that is nabla of f of w. So this is the gradient of the function. So we calculate the gradient of the function, and that represents the direction of greatest increase, and we just subtract that off. Okay, we just subtract that off. There's a scaling parameter here, it's gamma. Sometimes we use the character lambda, some value. Okay, this is some positive constant, a scaling factor. And we just say at the next iteration, at w at time n plus 1 is going to be our current w minus whatever some scale of the gradient. Right? And that's the entirety of the gradient descent algorithm. I think it'll make a little bit more sense once I give you some real numbers. We'll look at a real function and try this out. Okay, let me, before I do that, let me give you your first view quiz answer for today, which is the letter D. D as in dog. Let me just verify, actually. This is always my fear that I give you the wrong view quiz answers. I mean, it's not that big of a deal, because if I did that, I would just throw the view quiz away, so. But, okay, yes, D. D is the first answer. Okay, so we will start with this function, Okay. Now here it's a function of x1 and x2. Okay, and this is just some arbitrary function. But you know, perhaps in linear regression it might be a function of w0 and w1 or something. But here I've got a two-dimensional function. It's a function of x1 and x2, and we're going to find the gradient of f with respect to the vector x. Okay, so here I've got x1 squared minus 2x1 minus 0.5x1 x2 plus 2.5 x2 squared. I will take the gradient of this with respect to x. And that will result in a vector. X is a two-dimensional vector, x1, x2. So the gradient with respect to x is also a two-dimensional vector. Basically, the partial with respect to x1 and the partial with respect to x2. So what is the partial derivative of this with respect to x1? Well, it's going to be 2x1 minus 2 minus 0.5x2. So that's going to be the first component of our gradient. What's the partial derivative of this with respect to x2? That will be our second component. So this is 0, 0. We get negative 0.5x2 and 5x2. Is that okay? As far as getting the gradient of our function, two-dimensional function with respect to x, is a vector of partial derivatives. Okay. All right, so this is what the function, the contour plot of f looks like. Okay, and so we can, again, the picture is kind of like this this paraboloid. It's like a bowl, and it looks kind of like this, right? So top down, the contours look like this, and I don't know, the function looks kind of like this. Okay. So what we want to do is we want to find the local minimum, or in this case, it's going to be a global minimum. Probably somewhere like right here in the middle of this dot, yeah, something around, I don't know what, point something. Yeah, I don't know the coordinates. we want to figure that out. Okay, so what we're going to do is I'm going to just start off at some arbitrary location, -5, 4. All right, it doesn't matter, but we're going to start off at -5, 4. I think we're up here. Okay, I'm going to start off in this top corner, -5, 4, and we want to get down into this thing. So I'm going to start off in this corner, and we're going to do gradient descent. Okay, so the gradient, again, is this two-dimensional vector, derivatives with respect to x1 and x2. So the gradient was 2x1 minus 2 minus 0.5x2, right? That's from this slide. 2x1 minus 2 minus 0.5x2, comma, negative 0.5x1 plus 5x2. So we're going to start there. We're going to find what is the gradient at this location, -5, 4. What is the gradient at this location? So I just plug in -5 for x1 and 4 for x2. I plug that in here, and I get -10 minus 2 minus 2. I get -14. Okay, and then here I plug in -5 and 4, and over here, when you do that, we get 22.5. Is that okay? Getting this value, the gradient of f at the location -5, 4. Okay. I've picked an arbitrary step size of 0.1. Okay. So going back to this, we're going to take our current location, which is currently x1, x2, -5, 4. We're going to subtract off lambda times the gradient. So I plug in, this is the time, at time 0, okay, x1, x2 at time 0 is -5, 4. And then I'm going to subtract off gamma, which I've arbitrarily chosen to be 0.1, times the gradient. The gradient is -14, 22.5. Okay, when I do this, -0.1 times -14 is 1.4. -0.1 times 22.5 is -2.25. We're going to do that. -5 plus 1.4 is -3.6. 4 minus 2.25 is 1.75. Right. And so x1, x2 at time 1 is going to be this. I just want to kind of pause here and make sure everybody's okay with starting off at -5, 4 and ending up at -3.6, 1.75. The process to go about that. Okay, it required us to figure out the gradient. It required us to plug in the current values into the gradient, and then it required us to add gamma times the gradient to our current location. Okay, so this gives us a new coordinate, negative 3.6, 1.75. And let me just show you. Okay, so here is negative 5, 4, and this is negative 3.6, 1.75. So we have taken a step in this direction right here. Okay, this is just some code doing this in R. So here's our function, x1 squared minus 2x1 minus 0.5x1 x2 plus 2.5 x2 squared. The gradient of f will return a vector with two components. The first component being 2x1 minus 2 minus 0.5 x2, and the second component being negative 0.5 x1 plus 5x2. So it's going to return, this return is unnecessary, but just to emphasize that it's returning a vector of length 2 with two components, df dx1, so the partial derivative of f with respect to x1 and the partial derivative of f with respect to x2. So this is just the function. And then if I start off at negative 5, 4, and here's gamma, okay, I can plug in the start components into the gradient of f, and it gives me back negative 14.0, 22.5, which is what we found. And then if I say, take our starting point minus gamma times the gradient, this gives me the same value, negative 3.6, 1.75, which is what we found when we kind of solved it ourselves. Okay, and then again, plotting that, we started off at negative 5, 4. We end up at 3.6, 1.75. And that is one iteration of gradient descent. Okay, and so now, what do? I start here at negative 3.6, 1.75, and I follow the same process. We will find the gradient at negative 3.6, 1.75. If we do that, I get negative 10.0, negative 10.075 and comma 10.550. Okay, and here I'm going to take negative 3.6 minus 0.1 times this, plus 1.75 minus 0.1 times this. And this gives me a new coordinate, negative 2.5925, 0.695. All right, so this is just the next iteration. I'm just following the same process. If you were to plug in these values manually, you would get this. And if you were to multiply this by 0.1 and subtract these values from 3.6 and 1.75, you will end up here. And so if I plot that, the next iteration takes me to this location, negative 2.59, positive 0.695, which is right here. And I just do this over and over and over again. I'm going to do 20 iterations. Okay, and so I'm going to say, let's just start off at negative 5, 4. At each location, I will take my vector stored into locations and the ith row of locations, and then I'm going to update my x vector by doing x vector minus the gradient at the x vector. Okay, and then I'm going to just plot all of these as arrows. So 20 iterations starts off at negative 5, 4, and here's the first iteration, second iteration, third, fourth, fifth, sixth, seventh, eighth, and you can see it is pointing us to where the global minimum is. Okay, so I started off here, and then we're just going downhill, and downhill in this case takes kind of this curved approach, and we're approaching the global minimum of whatever this location is. Okay, is that all right? Here, we had been using gamma of 0.1. We can try using a smaller step size. So rather than taking a big step, I can take a smaller step size by changing gamma to be something smaller, to say 0.03. Okay, and now what does this look like? Okay, it looks very similar, except each step is smaller, and so after 20 iterations, I've only gotten this far. And so this will converge eventually, but it just takes a lot more iterations. I could take a bigger step size, so here is gamma 0.15, and I've taken a big step, and I get closer to the center a little bit faster. All right, so this was gamma 0.1, gamma 0.03, gamma 0.15, so that's fine. You can say, well, why don't we just take a big gamma? Like, let's converge as fast as we can. Okay? If you take gamma too big, then what happens is sometimes you overshoot. You overshoot, and you end up getting something inefficient. So you get the zigzag pattern. What's going on here? Okay? Well, basically, it said go in this direction. Go in this direction from -5, 4. Go in this direction as, you know, if you look at these lines, this initial vector, they're all pointing in the same direction. But here, how far should I go? Well, we went too far. We went so far. Okay, so when we started here, and we took a small step, and then, you know, we're still kind of going downhill. But over here, we took such a big step that we actually ended up like on the other side of the paraboloid. Okay, so you know this paraboloid is this bowl, and it's kind of just saying like which way is to the bottom. You're on one side, and you say, okay, well go north, and that will get you towards the bottom. But if you take too big of a step, you end up on the other side of the valley, where which way is downhill, and now the downhill direction is in the opposite. It goes south. Okay, and so we end up doing this, and we end up going back and forth, and this actually ends up being inefficient. Okay, sometimes you can even overshoot so much that that it points in the opposite direction, and it just doesn't converge at all. Okay, so remember, the gradient is a measure of not just the direction in which is greatest descent, but also kind of the magnitude, kind of the slope at that point, right? So if we have this paraboloid, okay, at the bottom, the slopes are shallow, right? If you look at just the bottom of the valley, there's only a small change in increase, right? But if you go, let me go back to this kind of three-dimensional picture. So at the bottom, it's very shallow. The amount of slope is quite low. But then as you go farther out, the slopes get steeper and steeper and steeper. And so the gradient is a function that points in the direction of steepest descent, but also the magnitude of the slope. And so what's going on here is we started on one side of the valley, and we've overshot the bottom, so we're on the other side now. But we overshot so far that we're actually higher up on the hill where the slope is even steeper. And so we ended up on the other side, and it says, oh, you got to go south, and you got to go, and it's even steeper, so the magnitude ends up even higher, and so you end up kind of like gaining speed going in the opposite direction. Okay, so that could happen, right? So what are we supposed to do when we choose gamma? Picking your learning rate can feel quite arbitrary, right? Picking a learning rate. A lot of it, there's a lot of trial and error. You try something out, and it doesn't work. And so the general recommendation, start small, 0.01, 0.001 or something, okay? And it's going to take a long time to converge, and then you say, well, okay, if it converges at a small rate, you say, okay, let's try increasing it a little bit, okay? And you try to keep increasing it until it kind of breaks, and you say, all right, I can't increase this anymore. It's not a great method. Okay, and there have been some algorithms that try to find a learning rate or a gamma or a lambda, whatever we want to call this, in a little bit more of a systematic way. But it's not easy, and I'll just say it still feels arbitrary at this point. Maybe eventually we'll get there, where we can say, all right, this is how we figure out the proper learning rate. But especially if your loss function is complicated, it might not be easy to define, right? For a simple loss function, we might be able to use some calculus and say, all right, this is going to give us a good learning rate. But for something quite hard, it might not be that straightforward. Okay, that's kind of gradient descent in a very, very, very quick introduction to that. I don't know if we have any questions on how this is working. Let me give you your second view quiz answer. The second view quiz answer today is C. C as in cat. C as in cat is our second view quiz answer. C as in cat. Okay, so let's try this out. We'll do gradient descent, not for an arbitrary function, but we're going to do it for ordinary least squares regression. Okay, so for ordinary least squares regression, we are going to try to minimize this function. This is our loss function. We want to find the values of the slope and intercept that minimize the loss function. Now I know, maybe we're already tired of this because we already know how to minimize OLS regression. We already know the answer is x transpose x inverse x transpose t, okay? Or we already know that it's going to be, you know, the correlation times the standard deviation of y over the standard deviation of x is their slope and things like that. We already know this, but what we're going to do is we're going to use gradient descent to just show you that we can still get to the same answer, okay? But again, gradient descent is an iterative algorithm, so it takes kind of a lot of computational cycles, and your answer is just going to be an approximation, right? All computational methods result in approximate answers, not exact ones. So if you're able to solve the answer analytically, analytic solution is almost always better. So it's silly to use gradient descent on something like least squares regression. But we're going to start off with least squares regression because we know this is going to give us a situation where we know the answer and we can say, all right, our method works and we got the answer. Whereas in the future, you're going to get situations where we don't have the analytic answer, and so we're going to just have to kind of rely on these approximation methods and say, well, it worked in the past, I hope it works now, okay? So again, using this for least squares regression, a little bit silly, but we're going to at least demonstrate that it works. So here is our loss function written in matrix notation. It's t minus xw transpose times t minus xw times 1 over n. And we are going to find the gradient of this, okay? And if I find the gradient of this with respect to, using non-matrix notation, okay, it requires us to find two components. The partial derivative with respect to w0, that is the intercept, and we find the partial derivative of the loss function with respect to the slope. Okay, so just expanding out what the prediction value is, the intercept plus slope times x1. I expand this out, and I take the gradient of this with respect to w0, and this is the gradient of the loss function, or the partial derivative of the loss function with respect to w0 gives me this value. The partial derivative of the loss function with respect to w1 gives me this. I'm going to kind of gloss over this, and you can review your notes on your own time to just say, yeah, these are the partial derivatives with respect to w0 and w1. We will use matrix notation, okay? And we've already done this on, I think on Friday or something. In one of the other lectures, oh, Thursday, I don't know. One of the other lectures, we found the gradient of the loss function with respect to w. So again, basically I expand this out, and then I take the gradient of this with respect to w, and this is what we have. Okay, and I think what we did the last time we said, well, here's the gradient, let's set it equal to 0 and solve for w. But we're not going to do that. We're going to just say, here's the gradient, and let's use the gradient to perform gradient descent. Okay, is that all right? So, what is the gradient descent algorithm? The gradient descent algorithm says take your current value of w, so this will be w0 and w1 at time n, and subtract off your learning rate gamma times the partial derivative of L with respect to w0 and partial derivative of L with respect to w1. And this will give us w0 and w1 at time n plus 1. Okay? Or, in matrix notation, we take our current value of w at time n, and we're going to subtract off gamma times the gradient of f at wn. and this will give us the value at our next iteration, the value of w at our next iteration at time n plus 1. Okay, so these two things say the same thing. Here we have just w in gradient, in matrix notation, and here we have it listed off as partial derivatives. Okay, so we are going to do a very simple simple example. Here is, I've got 3 points, 1, 3, 5, and the actual values, so x is 1, 3, 5, and the values of y or t are 4.8, 11.3, and 17.2. And if I were to solve this using just linear regression, the answer is our intercept should be 1.8 and the slope should be 3.1. So this is just the answer. This is the answer that we want to find. Okay? And again, using gradient descent in this situation is a little silly because we already have the answer. The intercept is 1.8 and the slope is 3.1. But I want to show you what we're going to do is we're going to start off at some arbitrary location and come to the solution. This is the plot of our data. So I got 1, 4.8, 3, 11.3, and 5, 17.2. And here is the fitted line. Okay, so this is a very simple data set, 3 points, and our fitted line looks like this. Okay, and this has an intercept of 1.8 and the slope of 3.1. Okay. In what we're going to do is we're going to code the algorithm, the gradient descent algorithm, and we'll do it in matrix notation. So the gradient of the loss function is negative 2 over n, x transpose t plus 2 over n, x transpose x w. This term, 2 over n, is just a comma, is just a constant. And basically, gamma here is also an arbitrary constant. And so we can account for this value 2 over n by kind of scaling our gamma to be larger or smaller, because it's just another constant here. Okay, so the gradient of the loss function, coded up, it'll be x transpose, negative x transpose times t plus x transpose x times w. Right, is that okay? Writing the gradient of our loss function right here. Okay, and the algorithm, again, is just this single line. Take your current value of w, subtract off gamma times the gradient. And that's it. And so here, I'm going to just start off with an arbitrary starting location. We're going to start off with an intercept of -1 and a slope of 1.5. All right, I'm going to set my gamma to be 0.02, and then I'm going to just let this run for 1,000 iterations. And after 1,000 iterations, it comes to the answer 1.79995 and 3.100001. Okay, so the true answer was 1.8, 3.1, and we got something close to that. Right, we got 1.79995 and 3.100001. Okay, and so that tells me our gradient descent algorithm did a pretty good job of approximating the true solution. Okay, it gave us a pretty good approximation of the value of the intercept and the slope that minimize the actual function. This is after 1,000 iterations. Okay, so again, it's not the most efficient method, right? We already have the solution, so obviously we should have just used that. But a lot of times these are our only options, is to use some kind of computational, iterative computational approach to get solutions where we can't do the analytic reaction. Okay, so let me just show you what this looks like. Okay, I'm going to show you a contour plot. The contour plot is a little bit strange to conceptualize. Okay, it is a contour plot showing what is the loss function, that is the mean squared error for, or I guess the, it might be the total sum of squares or the mean squared error. I don't know, they're just scalar multiples of each other. for different slope and intercept values. The minimum occurs when the intercept is 1.8 and the slope is 3.1. And so we're going to have different values of the loss function for different values of the slope and intercept. So this is just kind of code used to kind of plot this. And so this function, or this plot, represents what is the loss function for different values of the intercept and different values of the slope. The minimum, okay, that is, so I hope this is okay. We're okay at looking at contours and recognizing that the minimum is going to be kind of at the center of this circle. Okay, the minimum is at the point where the intercept is what? Is at 1.8 and the slope is 3.1. And if we pick a different intercept, say an intercept of 2 and a slope of 2, we're going to have quite a different value of the loss. Okay, and so I'll illustrate. This is the path that our algorithm took. We started off at some arbitrary intercept of -1 and a slope of 1.5. And by using gradient descent, it followed this red path. It went up, 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 and then it started coming back down. And it came down to something very close to 1.8, 3.1. Okay? Came close to 1.8, 3.1. We started off at -1 with an intercept of -1 and a slope of 1.5. So let me just show you what this looks like, okay? So here are our 3 points, okay? These were our 3 points. I forgot what they were, 1, 4 point something, and 3, 11 point something, and 5, 17 point something, right? So these were our 3 points. And here I started off with an intercept of -1 and a slope of 1.5. So the fitted line has a slope of 1.5. Okay, the fitted line has a slope of 1.5. And so I don't know if I can draw on this, but basically, how do I do this? You respect my privacy. Okay. Oh, this is taking too long. I just want to draw on my screen. Okay. All right, let's do full screen. Windows key Shift S. Windows key Shift S. Did that work? Draw a shape to create a snip. Oh, gosh. Oh my gosh. Can I just draw on this? No, I probably can't. Okay, never mind. Basically, we're taking the residuals between this and we're going to create a square, right? So here are our residuals between the actual and the thing. So, you know, we get a squared residual of this. So this is going to be a huge sum of squared residuals, right? Between this and this and this, okay? And so we're going to take this, and at the next iteration, doing gradient descent, okay, we say, you know what? We need to increase the slope. Okay, we need to increase the slope, we need to increase the intercept. And so at the next iteration, it says, and we took a step in that direction, and it says, you know what, here's your slope, 2.3, so the line got steeper, right? It used to be slope of 1.5, and we increased the slope, we increased the intercept, so now this is our new line, okay? So if I do this, is going to work. Okay, so now we can see, all right, the squared residuals got a little bit smaller. Something. Okay. So we're getting some improvements. The idea here is that we're getting some improvement in something here, okay? So you compare this versus this. Our slope, our total squared residuals is getting smaller, so we're getting closer to the minimum, okay? It still says we need to keep increasing the slope. This slope is not steep enough, okay? So after a few more iterations, after 5 iterations, okay, it says, all right, we're doing better, okay? Our slope is now 3.33, okay? So this is actually, our slope is a little bit too high, okay? And it says, you know what? Now we need to kind of start increasing the intercept, okay? So we're a lot closer. Our sum of squared residuals is a lot less than it used to be, okay? Because we're looking at the difference between each dot and the line. It's a lot smaller, okay? And I keep going. So now we've reached kind of the peak slope, right? The slope is 3.63. And we can say, okay, that's a little bit too steep, right? So this line is a little too steep for the data. But it's doing a lot better than it used to be, right? This is where we started off. Now we're here, okay? We're doing a lot better. And we're trying to figure out, okay, we need to figure out the right combination of intercept and slope. So what do? We're going to start increasing the intercept. So you can see in the beginning, the amount we increased the intercept wasn't that much. We had to rapidly increase the slope. And now we're going to try to adjust back down. So what do? We're going to start increasing the intercept. And every time we increase the intercept, we say, oh, you know what? We can make the thing just a little bit less steep. Okay, we can make the line a little bit less steep. And so here I go. So we're going to increase the intercept, make it a little bit less steep, increase the intercept, make it a little bit less steep. And this is kind of the path that we've taken. Okay, and obviously there's still more improvement that can be done. We can keep increasing it, increasing the intercept and decreasing the slope, and we'll eventually get to that solution of 1.8, 3.1. So this is after 300 iterations. It took us a while to get here, but here we have a line that does a lot better job of fitting our 3 data points than what we started off with. We just started off with this arbitrary and terrible line of having a intercept of -1 and a slope of 1.5, and we said, okay, well let's do this, okay? And we got here. If we let it run, we'll get something close to the actual solution of intercept of 1.8, slope of 3.1. Does that kind of make sense? Okay, so here is one where I picked a gamma that was too big, and I got this kind of wiggle-waggle business. So here we said, oh, you know what? We gotta increase the slope. I started off with a slope of 1.5, and we said, we need to increase the slope. And so we shot off in the wrong direction. We said, all right, let's go with a slope of 6, okay? We go, no, that's too much, all right? And then bring it down, okay. And then it goes, okay, we bring it down, 2. Oh, not enough, bring it up, right? This is kind of just like, it's like adjusting the shower, right? You have it on one side, it's like, oh, too cold. You bring it up, oh, too hot. And then you got to kind of like wiggle back and forth. And then you get, oh, okay, now it's a good spot, right? Or I mean, if you go to a luxury hotel where they have a really nice shower, then you might have a little bit more of a controlled thing where you say, oh, you know what, let's just adjust it, and it slowly increases to a nice temperature. They might even have buttons that you push, right? Just push the button and it brings up the temperature. You're like, oh, this is nice, right? But sometimes, you know, depending on what apartment you're in, your shower might act like this, and you have to kind of go back and forth and try it, right? So this is not ideal. This is too big of a gamma, right? Here is something where it's just like the opposite, where you get kind of like this crazy feedback where it just starts going off crazy, and here you don't even converge. It just goes off all over the place here. Okay. I am going to run out of time. Let me give you your last view quiz answer. E as in elephant. E as in elephant. Okay, this is an important topic though. When we calculate the gradient, sometimes we're not sure if we got the right answer. And we want to be able to check, did I get the right answer, right? And a lot of times when you do math, and it's complicated and hard, you think, this is the answer I got, but I'm not quite sure if it's right. So here's a tool to kind of help you figure out if you got it right or wrong, okay? And we're basically doing a little bit of just a numeric version of the derivative, okay? So basically, we say, well, what is the definition of the gradient? The gradient is the partial derivative of f with respect to your first component, partial derivative of f with respect to the next component, partial derivative of f with respect to, basically each component. And so what we're going to do is we're going to say, okay, well, the partial derivative, okay, for the first component, with respect to the first component is, let's take the function of f, add a small value, h. Add a small value, h, to x1. We leave x2 untouched. And this is key, all right? For the first component, don't do anything to x2. Only add h to x1, okay? And then subtract off the function at x1, x2. And then you divide by the size of h. Do the same thing for the second component. This time, for the second component, again, very important, you don't touch x1. x1 remains unchanged. The only thing that we're going to add h to is x2. Okay, we add h to x2, and we see how much it has changed. So, if I wanted to do this, what is the numeric gradient for at the point -5, 4? Okay, first I plug in what is the value of the function at this point, -5, 4. When I plug in the value -5, 4 at this location, I get a value of 85. I get a value of 85. All right, and I'm sorry, I'm going to go 1 minute over my time here. Okay, so my gradient is going to have two components. First, I'm going to add just a small value. Here I'm adding 0.01, which is unusually large. Usually it's something like 10 to the -5 or 10 to the -6. But here we're going to add just 0.01 so we can illustrate this. And I'm going to add 0.01 to the first component. Okay? So -5, 4 gives me a value of 85. But I'm going to plug in -5 plus 0.01. So I'm going to plug in -4.99, 4. And we see, so again, x2 remains unchanged. x2 remains 4. Okay, I don't touch the 4 here. And I say, well, okay, what is the value of the function when I plug in -4.99? If I plug in -4.99 into the function, I get 84.86. Okay, how much is that? That's a change of, -0.1399. I divide by 0.01 and I get -13.99. Okay, same thing on the other side. I leave the -5 unchanged over here. I add a 0.01 to x2. I get 4.01. I plug in -5, 4.01. How much does it change? It goes from 85 to 85.225. 0.225 divided by 0.01 gives me 22.525. And so my numeric estimate of the gradient, okay, kind of my numeric check gives me -13.99, 22.525. Where if I go back to one of the older slides, I think the analytic result of the gradient was -14, 22.5. Okay, so that aligns, and this is a way for you to kind of check, did I calculate my gradient correctly, and to kind of verify this. Okay, we will end here. I think I gave you all 3 view quiz answers, so we'll end here. Have a good rest of your day. We'll see you on Friday.